Chapter 1, The Clouds Over the Clockwork Universe. Before we embark on this journey through the minds that unraveled the fabric of reality, please subscribe to the channel right now and enable notifications so you do not miss the next episodes of this scientific saga, and if you enjoy exploring the history of human knowledge, leave a like to support our work. The story of modern physics begins not with a discovery but with a feeling of completion that permeated the scientific world at the end of the 19th century. As the year 1900 approached, the great physicists of Europe believed that the major work of describing the universe was essentially done, and the laws of motion established by Isaac Newton 2 centuries earlier ruled the heavens and the earth with absolute precision, portraying a universe that operated like a perfect clockwork mechanism where every planet and every falling apple obeyed a deterministic script that could be calculated and predicted. In this comfortable era of classical physics, we also had the brilliant equations of James Clerk Maxwell, which had unified electricity and magnetism into a single elegant theory of electromagnetism, and it seemed that light itself was merely a wave rippling through an invisible medium called the ether, and so the grand structure of science stood on two mighty pillars, which were Newtonian mechanics for matter and Maxwellian equations for radiation, and many professors advised their students not to pursue physics because there was nothing new to be discovered, only more precise measurements of what was already known. However, there was a man named Lord Kelvin who was a titan of Victorian science, and in a lecture at the Royal Institution he pointed out that there were two small clouds on the horizon of physics that obscured the beauty and clearness of the dynamical theory, and he believed these clouds would soon be blown away, but he could not have known that inside those small clouds lay a storm that would destroy the entire foundation of classical physics and rebuild the universe in a way that defied all common sense. The first cloud was related to the nature of light and motion, and the second cloud, which is the focus of our first chapter, was known as the Ultraviolet Catastrophe, and it arose from a simple question about how hot objects emit light and heat. For instance, when a blacksmith heats a piece of iron, it glows red, then orange, then yellow, and finally white as it gets hotter, and the physics of the time tried to calculate the energy emitted by a theoretical object known as a blackbody, which is an idealized absorber and emitter of radiation. According to the trusted equations of classical thermodynamics and electromagnetism, as an object got hotter it should radiate an infinite amount of energy in the ultraviolet range of the spectrum, which was an absurd prediction because if it were true, every time you opened an oven door you would be blasted by a wave of lethal radiation and the universe would be uninhabitable. So clearly the theory was wrong, but no one could explain why the math led to infinity while reality remained safe and stable. Enter Max Planck, a conservative German physicist who had no desire to start a revolution but simply wanted to solve this annoying discrepancy, and he worked tirelessly in Berlin trying to force the classical equations to match the experimental data, but nothing worked, and out of sheer desperation Planck decided to try a mathematical trick that went against everything he believed in about the continuous nature of energy. Planck proposed that perhaps energy did not flow in a continuous stream like water from a tap, but instead was emitted in tiny discrete packets or chunks, which he called quanta, and this was a radical idea because in the classical world energy was always smooth and continuous, but Planck assumed for the sake of calculation that energy came in little grains, and he wrote down a simple equation where energy equals a constant multiplied by the frequency of the radiation, and this constant would later be known as Planck's constant. To his amazement, when he applied this strange assumption of quantized energy to the black body problem, the absurd infinities disappeared and the equation matched the experimental data perfectly, and Planck had solved the ultraviolet catastrophe. But he did not believe that these quanta were real, and he thought they were merely a mathematical convenience, a formal device to get the right answer, and he spent years trying to find a way to get rid of them and return to the smooth physics of the past. But the genie was out of the bottle, and the year 1900 marked the birth of quantum mechanics. Although nobody realized it yet, not even Planck himself, for the world was still asleep in the comfort of certainty, unaware that the ground beneath their feet had just turned into shifting sand, and that the rules of cause and effect were about to be challenged by a new generation of thinkers who would look into the heart of the atom and find they're not a solid machine but a world of ghosts and probabilities. While Planck struggled with his own discovery, a young man was working in a patent office in Bern, Switzerland, far removed from the prestigious universities and laboratories, and his name was Albert Einstein, and he was about to take Planck's mathematical trick and prove that it was physically real, and in doing so he would shatter the second cloud that Lord Kelvin had mentioned and plunge the world into a new era of relativity and quantum weirdness. But that is where the true conflict begins, because the very man who would prove the existence of the quantum would spend the rest of his life fighting against the chaos he helped unleash. The scientific community ignored Planck's quanta for 5 years, viewing it as a niche solution to a specific problem regarding heat, but the concept that nature is grainy and not smooth was a fundamental assault on the continuity of the universe, and if energy comes in packets it means there are jumps in nature where an object changes its state without passing through the states in between, which is a concept so alien to human experience that it is hard to visualize even today. Thus the 20th century began not with a fanfare but with a quiet equation written by a reluctant revolutionary, and the stage was set for the greatest intellectual drama in history, where the nature of light, the structure of matter, and the definition of reality itself would be fought over in the lecture halls of Europe, and the clockwork universe of Newton was ticking its final seconds before exploding into a kaleidoscope of uncertainty, and the man who would light the fuse was currently checking patent applications for electromagnetic devices, dreaming of riding alongside a beam of light. Chapter 2, The Miracle Year and the Atom. The year 1905 is known in the history of science as the Annus Mirabilis, or the Miracle Year, because in the span of just a few months the unknown patent clerk Albert Einstein published 4 papers that would forever change our understanding of space-time, mass and energy. And while he is most famous for the theory of relativity and the equation E=mc², it was his paper on the photoelectric effect that truly launched the quantum revolution and earned him the Nobel Prize. The photoelectric effect was a phenomenon where shining light on a metal surface caused electrons to be ejected from the metal, but the strange thing was that increasing the intensity of the light did not make the electrons fly off with more energy, which contradicted the wave theory of light, because if light were a continuous wave, a brighter light should hit the electrons harder, like a big ocean wave hitting a surfer, but instead it was the color or frequency of the light that determined the energy of the electrons. Einstein looked at Planck's idea of energy packets and took it seriously, proposing that light itself was not just a continuous wave but was made of particles which we now call photons, and he argued that each photon carried a specific amount of energy determined by its frequency, and when a photon hit an electron it transferred that energy like a billiard ball colliding with another, and if the photon had enough energy the electron was knocked free, but if the photon had too little energy no amount of brightness would matter, because individual photons were too weak to dislodge the electron. This was a heresy to the physics establishment, which had spent 100 years proving that light was a wave, but Einstein's particle theory explained the experimental data perfectly, and it meant that the quantization of energy was not just a mathematical trick used by Planck but a fundamental feature of reality, and light had a dual nature, behaving sometimes as a wave and sometimes as a particle depending on how you looked at it, and this wave-particle duality would become the central mystery of quantum mechanics. While Einstein was rewriting the laws of light, a physicist from New Zealand named Ernest Rutherford was busy in Manchester dismantling the accepted model of the atom, because at the time scientists believed the atom was like a plum putting a positively charged sphere with electrons embedded inside it like raisins, but Rutherford decided to test this by firing alpha particles at a thin sheet of gold foil, expecting them to pass right through, with only minor deflections. To his shock, most particles went through, but some bounced straight back as if they had hit a solid wall, and Rutherford famously said it was as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you, and he realized that the mass of the atom was not spread out but concentrated in a tiny dense center called the nucleus, and thus the solar system model of the atom was born, with electrons orbiting the nucleus like planets orbiting the sun. But there was a fatal flaw in Rutherford's model, because according to classical physics an electrically charged particle moving in a circle should emit radiation and lose energy, spiraling inward and crashing into the nucleus in a fraction of a second, which meant that if classical physics were true, every atom in the universe should instantly collapse and matter should not exist, and yet here we are made of stable atoms, so once again, the old laws failed to explain the new reality. Into this crisis stepped a young Danish physicist named Niels Bohr, who had gone to work with Rutherford and possessed a mind that was not afraid to break the rules, and in 1913 Bohr proposed a radical new model of the atom that incorporated Planck's and Einstein's quantum ideas, stating that electrons could only orbit the nucleus at specific fixed distances or energy levels, and they were forbidden from existing in the space between these orbits. Bohr declared that an electron could jump from one orbit to another without traversing the space in between, a phenomenon that became known as the quantum leap, and when an electron jumped from a higher orbit to a lower one it emitted a photon of light with a specific color, and when it absorbed a photon it jumped to a higher orbit, and this explained why elements emit light only at specific frequencies, creating a unique barcode or spectrum for every element in the periodic table. The Bohr model was a triumph because it saved the atom from collapse and explained the colors of the world, but it came at a high price because it required physicists to abandon the idea that motion was continuous and accept that electrons simply teleported between states, and there was no mechanical explanation for why this happened or how the electron knew where to go, and it was simply a rule imposed by the quantum nature of the universe. Einstein praised Bohr's work as a work of musicality and supreme intuition, but he was deeply troubled by the implications, because if things happened without a mechanical cause then the strict determinism of physics was eroding and the universe was beginning to look less like a clock and more like a game of chance, and although Einstein had started the revolution he began to feel that physics was taking a wrong turn into irrationality. As the 1920s approached, the quantum theory was a patchwork of classical ideas and new quantum rules stitched together by the genius of Bohr and Einstein, but it was not yet a complete consistent theory, and the next generation of physicists, young, brilliant and arrogant, was about to enter the scene, and they would push the quantum logic to its ultimate and terrifying conclusion, stripping away the ability to visualize reality at all and leading to a clash of titans that would divide the scientific world. The atom had been saved, but the nature of the electron was still a mystery, and the question remained as to whether it was a particle or a wave or something else entirely, and the answer would come from two different men who hated each other's theories and who would create two different versions of quantum mechanics that were mathematically equivalent but philosophically opposite, creating a schism that demanded a resolution at the highest levels of science. The stage was now set for the Roaring Twenties, not just in culture and economy but in physics, where the old guard represented by Einstein and Planck would face the young revolutionaries led by Bohr, Heisenberg and Pauli, and the battleground would be the nature of reality itself, and the weapon of choice would be high-level mathematics that described a world so abstract that no human mind could truly picture it. Chapter 3: The Waves of Probability and the Death of Certainty. The revolution entered a strange new phase in 1924 with a French prince named Louis de Broglie, who was studying for his doctorate and asked a simple but profound question, implying that if light, which everyone thought was a wave, can behave like a particle, then perhaps matter, which everyone thinks is made of particles, can behave like a wave. De Broglie proposed that every electron and every atom, and indeed every moving object, has a wavelength associated with it, and although this seemed ridiculous for large objects like baseballs, for tiny particles like electrons the wave nature was significant, and this idea captivated Albert Einstein, who gave it his stamp of approval, bringing the thesis to the attention of the scientific world and setting the stage for the next great duel. In Zurich, a physicist named Erwin Schrödinger read about these matter waves and decided to find the equation that governed them, and legend has it that he went on a ski trip to the Swiss Alps with a mysterious mistress and plugged his ears with pearls to block out the noise, and when he returned he had discovered the wave equation, which is now the most famous equation in quantum mechanics, and it described the electron not as a particle bouncing around but as a wave spreading out around the nucleus like a vibration on a drum skin. Schrödinger's wave mechanics was beautiful and continuous, and it appealed to many physicists because it allowed them to visualize the atom again, and it seemed to restore the smooth order of classical physics and remove the jerky quantum leaps that everyone hated so much, and Schrödinger hoped that his waves represented the physical density of the electron smeared out in space. However, at the same time in Germany, a young and ambitious genius named Werner Heisenberg was taking a completely different path because he suffered from severe hay fever and retreated to the treeless island of Helgoland in the North Sea to escape the pollen, and there, working day and night in a feverish state, he decided to discard all pictures and visualizations of the atom because he believed we can never see the orbit of an electron, so we should not try to describe it. Heisenberg built a theory based solely on the observable quantities like the frequencies and intensities of light emitted by the atom, and he used complex tables of numbers which mathematicians call matrices, and his result, known as matrix mechanics, was abstract and difficult and completely unvisualizable, but it predicted the results of experiments perfectly, and thus physics was split in two, with Schrödinger offering a visual wave and Heisenberg offering a mathematical matrix, and the two men despised each other's theories, with Heisenberg calling Schrödinger's waves disgusting and Schrödinger saying he was repelled by Heisenberg's math. The resolution came from Max Born, who looked at Schrödinger's wave function and realized that it did not represent the physical electron itself but rather a wave of probability, meaning that the wave described the likelihood of finding the electron in a particular place, and this was the birth of the statistical interpretation of quantum mechanics, which stated that nature is inherently probabilistic and that at the fundamental level we cannot predict exactly what will happen but only the odds of it happening. This was the moment Einstein began to pull away because he famously declared that God does not play dice with the universe, for Einstein believed in a reality that existed independently of observation, where an electron is always somewhere and moving at some speed regardless of whether we are looking at it, but the new quantum mechanics said that until you measure it, the electron has no definite position but exists in a superposition of all possible places at once. Then in 1927 Heisenberg delivered the final blow to classical determinism with his uncertainty principle, which showed that there is a fundamental limit to what we can know, because the more precisely you measure the position of a particle, the less precisely you can know its momentum, and this was not a fault of clumsy instruments but a fundamental law of nature, implying that the universe does not possess precise values for all its properties at the same time. This meant that the dream of the clockwork universe was dead, because if you cannot know the present state of the universe with perfect precision, you cannot predict its future, and causality itself had been loosened and the rigid laws of Newton were replaced by a haze of possibilities where things happen without a strict cause and where the act of observation changes the reality observed. The scientific community was reeling from these shocks, and the divide between the old guard and the new generation grew wider, and everyone knew that a confrontation was inevitable, and it would happen in Brussels at the most famous scientific meeting in history, where the heavyweights would enter the ring to decide the fate of reality itself. Chapter 4: The Solvay Duel and the Quantum Legacy. In October of 1927, the world's greatest physicists gathered in Brussels for the 5th Solvay Conference, and the photo taken at this meeting is perhaps the most intelligent photograph ever captured, featuring 17 Nobel Prize winners including Einstein, Bohr, Curie, Planck, Schrödinger and Heisenberg, and the atmosphere was electric because the debate was no longer just about atoms but about the nature of existence and the role of the observer. The conference turned into a legendary duel between Albert Einstein and Niels Bohr, and every morning at breakfast Einstein would present a clever thought experiment designed to break the uncertainty principle and prove that quantum mechanics was incomplete and inconsistent, and he would construct imaginary devices with clocks and shutters and scales trying to show that one could measure the position and momentum of a particle simultaneously and trap nature in a contradiction. Niels Bohr would listen carefully and often appeared flustered and mumbled to himself, and he would spend the entire day and evening discussing the problem with his young colleagues Heisenberg and Pauli, and by dinner time Bohr would always have a solution, and he would prove to Einstein that his thought experiment failed, often using Einstein's own theory of relativity to refute him, and day after day Einstein tried to find a flaw in the quantum logic, and day after day Bohr defeated him. By the end of the conference Einstein was defeated but not convinced, and although he could not find a mathematical error in the new physics, he simply refused to accept its philosophical implications, creating a stubborn resistance that would last until the end of his life, and he spent his remaining years searching for a unified field theory that would unite gravity and electromagnetism and restore deterministic order to the universe, a quest that ultimately failed but showed his unwavering commitment to the idea of an objective reality. The interpretation that emerged from this conference became known as the Copenhagen interpretation, named after Bohr's institute, and it stated that questions about what the electron is doing when we are not looking are meaningless, and that physics is not about nature itself but about what we can say about nature. And despite its weirdness, this view became the standard dogma of physics taught in universities around the world for decades. But the story did not end in 1927, because while the philosophical debate remained unresolved, the mathematical machinery of quantum mechanics proved to be the most successful theory in the history of science, predicting the behavior of the subatomic world with an accuracy that is equivalent to measuring the distance from New York to Los Angeles to within the width of a human hair. This strange theory of waves and probabilities and uncertainty is the foundation of our modern world, because without understanding the quantum rules of the electron we could not have invented the transistor, and without the transistor there would be no computers, no smartphones, no internet, and no digital age, and other technologies like lasers and MRI machines and nuclear energy and LED lights all rely entirely on the principles discovered by that small group of men in Europe between 1900 and 1930. Yet the mystery remains, and the ghosts that Einstein feared are still with us, and today physicists are still debating the meaning of the wave function and exploring new interpretations like the many worlds theory, which suggests that every time a quantum event has multiple possible outcomes the universe splits, and all of them happen in parallel realities. And we are also on the verge of a second quantum revolution with the development of quantum computers, which harness the strange power of superposition to solve problems that traditional computers never could. The journey from the clockwork universe to the quantum cloud is the greatest intellectual adventure of our species, showing us that the universe is far stranger and more wonderful than we ever imagined, and that the solid reality we perceive with our senses is merely an illusion created by the dance of invisible particles and waves, and that at the heart of everything lies a mystery that beckons us to keep asking questions. We stand on the shoulders of these giants who dared to look into the abyss of the atom and did not blink, and their story reminds us that knowledge requires the courage to let go of our most cherished beliefs, and that the truth is often found not in the light of certainty but in the shadows of doubt. Thank you for joining us on this long journey through the history of science, and if you made it this far, please comment the phrase "God does not play dice," so I know you are a true explorer of knowledge, and do not forget to share this video with anyone who loves science, and subscribe for more deep dives into the mysteries of the universe. And until next time, keep looking up and keep wondering.